In this video, I'm going to show you the workflow in order to perform a DOE using parametric CAD within SimLab. In many cases, we are interested in finding the effect of change in CAD features, for example ribs thickness, on the final results. Currently, this is supported for models created using Inspire parametric feature. The objective of this example is to study the effect of fins dimensions and distance between them on heatsink heat transfer performance. So the first step is to open Inspire. So you have to import your file or to create from scratch your CAD. In this case, I have created the base and the top plate of the heatsink in order to generate some fins on the top of the plate. So let's go to Sketch and click the rectangular option. I'm going to create a rectangular in the middle of the top plate. The thickness of the fins is considered as a parameter, so I'm going to specify t equal 4 mm and exit this function. Let's go to Geometry ribbon. I'm going to use the Extrude tool in order to extrude this profile. Make sure to activate the new part in order to have a separate part for the fins and for the plate in the model browser. The height of fins is as well a parameter, so h equal to 10 mm, and exit this function. In order to create the pattern, I'm going to use the linear pattern function. I'm going to select the part, and I'm going to choose to create the pattern in both directions. Firstly, I have to select the first direction. The distance between the fins is considered as a parameter, and I'm going to create 4 copies. Let's do the same for the other direction. Select the second direction, choose the same distance for the other direction, and choose 4 copies. A good idea here is to combine all these parts of the fins in one component in the model browser, just for simplicity. So I'm going to choose the Boolean tool, I'm going to select all the fins and click Combine. Now I have one part for the fins and I can rename it as well. In order to make sure that my parameters are correctly assigned, I can go to Variables and I can make some slight alterations in the values of each parameter in order to see what will be the result. For example, increase the thickness to 5, increase the height from 10 to 15, and in this case I'm going to decrease the distance from 9 to 8. Let's save our Inspire file. Now let's go to SimLab. Before I actually go and import my Inspire file, I have to start the recording. I'm going to go to Automation, Scripting and Record. By clicking Record, each and every step that I will do during the recording period will be captured, and in that way I can use this Python script in order to perform a DOE later on. The recording has just started and I can go to import my Inspire file. I'm going to drag and drop my Inspire file, and automatically the parameters that I have just created will be imported as well. If I go to parameters, you will see that our CAD parameters are imported as well. So now let's go and create a solution. I'm going to go to Solutions and create a thermal steady state heat transfer analysis. The first step is to create the mesh. I'm going to use the automatic 3D TET mesh, and I'm going to use 1 mm as an average element size and just keep the default options for the rest, just for simplicity. Volume mesh is complete, and now we can assign the mesh that we have created into the relevant solution. After that, we can assign some material properties to my two components, so I can go to Property and import two XML files that I have created previously. One for aluminum and one for copper. I want to have to the fins region aluminum, and for the base, I'm going to assign copper. In SimLab, we can create from scratch some material properties by clicking Material tool, or we can even use some already defined material that are included in the SimLab material database. The next step is to create some loads and constraints. First of all, I want to create a contact between the two parts, so I'm going to use the auto contact. I'm going to keep the freeze option for contact type, and I'm going to have a surface-to-surface contact. Next, I want to apply a flux on the surface of the base of 0.3 watt per square millimeter. Apart from that, I'm having a free convection to the outer surfaces of the heatsink, except from the face from which the heat is generated. I'm considering an ambient temperature of 20 degrees and a convection coefficient of 0.001. My setup of the solution is complete. I'm going to select the solution folder, and also to the settings, if I go to Format and Execute options, I can select the number of processors. Now I'm ready to run my analysis. I will go to Results, right-click, and Update. The thermal solution has just started. Our simulation now is complete, and we can have a look on the results and more specifically on grade temperature. We can also visualize the results at a specific region of interest. In this case, I'm interested in the fins region, so I'm going to select the option Selected Displayed. In that way, I can visualize the temperature range only in this specific region. I can also make some alterations in the contour options, for example, to change the color from discrete to continuous. Now, let's exit the results, and I'm ready to stop my recording and save it to the relevant folder. If I open now a new session, I can use the Python script that I have just saved in order to perform all the steps from the beginning until the end without the need from my side to do anything. So I'm going to click Play, Auto, and choose the Python script that I have just saved. This will take some time to be complete, since it will start with import of Inspire file, performing a thermal simulation including the material characterization, loads and constraints application, and results visualization. The Python script has run, and now I'm at the same stage at which I stopped my recording. So now the next step is to create the response for my parametric DOE analysis. So I'm going to go to Results, right-click on Grid Temperature, and create a response. In this specific example, I'm interested in minimizing the maximum temperature only in the fins region. So the response will be the temperature in the fins region, and more specifically, I want the maximum value in this region, and click Create. Now let's go and do our parametric DOE analysis. Go to Solutions, DOE, Parametric DOE. The first step is to choose our project file, which is our heatsink script that we have saved. After that, we have to enable the parameters are mostly interested in, and I have to specify the range for its parameter. For example, for the thickness 2 to 5, for the height 2 to 15, and for the distance between the fins 6 to 9. I'm also able to increase the level for each parameter in order to increase the number of runs. In this case, let me make it 4 for each parameter and create the experiments. So now 64 experiments have been created, and I'm ready to start my DOE. This will take some time to be complete, since it will run 64 analyses with different combinations of distance between the fins, height, and thickness of fins, in order to see what will be the maximum temperature in the fins region, with a target to minimize this value. The DOE analysis is now complete, and we can have a look on the results in order to understand what is the optimum solution for the distance, height, and thickness in order to minimize the maximum temperature in the fins region. More specifically, if we go to the round 61, the maximum temperature will be minimized, so this is the optimum solution. We can even post-process the results in HyperStudy, and automatically the software will be opened and the setup will be complete. And we can go directly to post-process the results. For example, we can go to Pareto plot in order to understand the influence of each parameter to the temperature in the fins region. The height and the thickness have a negative correlation with the temperature, whereas the distance has a positive correlation. Also, we can study the interactions, where we can study the effect of two variables moving simultaneously. The outcome of this example is that our temperature in the region of the fins will be minimized if we maximize the height and the thickness, and we minimize the distance between the fins. The results is actually, it was actually expected since the area of the fins will be maximized, and so we will have the optimum result. Thank you.